Okay, so we are in our final lecture for kinetics of particles, impulse and momentum. If you look at your schedule, you will have this lecture on today, impulse and momentum. And the next lecture session will be just the test, okay? So because next week is already the final week before the semester break starts, right? So I'm pretty sure everyone's looking forward to go back balik kampung, kan? So I'm not going to bother with long classes up to 11, 12 o'clock. So hopefully we can do that. Let's try to speed up things. Recap on the particles, kinetics, work and energy. Remember last time there were several types of force that will result in work, and this force must act in the direction of motion. It can act on an angle, right? But as long as the angle is not 90 degrees, remember we have cosine 90 is 0, so it's fine as long as you don't have the angle of the force and the motion to be 90 degrees from each other. So you will get a value of work, and that will be identified by the letter U from position 1 to 2, U sub 1 dash 2. All right. So we had constant force, and then we had work due to variable force, where you cannot treat the F cosine theta as a constant like you do in the first one. You see the first one here, you can just omit the integrand and let's say put everything else out of the integral. F cosine theta and ds becomes s minus 0, right? So s minus 0 is just basically the displacement s. Now you have the variable force, whereby you cannot simply remove the integration part there. You have to integrate the function of force with respect to, let's say, the displacement. F is a function of time, F is a function of something, right? So then you have work due to weight, okay? Then you have spring work, and then you have work due to friction. So friction-wise, you need to calculate the normal force. Although normal is perpendicular to the direction of motion, it will not result in any work, but it is useful to find the friction force, because friction force depends on the normal force, right? Okay. Then when we have found all the work done based on the many forces that we identify based on our free body diagram, then we can plug in our principle of work and energy. Your T1 equals summation of U 1 to 2. T1 plus the summation of work from 1 to 2 equals to T2. The kinetic energy is represented as T. Remember, your kinetic energy is half times mass times velocity squared, and you have to specify at point 1 and point 2. Okay, so basically those were what we covered, but I actually did not on purpose cover conservation of energy, because what we will do today in this class is to cover also conservation of energy. So I wasn't planning on doing things double or redundant. So we will look at conservation of energy in this session. And by conservation of energy, it's pretty simple. You have T, which is your what? T is what? T is your kinetic energy, isn't it? All right, so V is what? V is the potential energy. In any problems related to energy, right, you have to look in terms of potential and kinetic energy. Why? Potential and kinetic energy, they are related to one another. So you have, let's say a ball, right? What is it doing there? Okay, so this ball, if let's say it's at the verge of a building, right? Just using example of a ball. Then at this point, there is potential energy, right? There is no kinetic energy. Kinetic energy over here is 0, right? It's not moving. So it's at the verge of falling, right? And you have, apart from kinetic energy, is the potential energy. You have some potential energy that's going to be mgy, right, from your high school physics. Potential energy equals the mass times gravity times the height where the object is falling, right? So this is why, okay, this object has a mass and g is basically 9.81, right? So it depends on the height of the object before it experience fall. Now, when it goes mid-air, right? So it falls somehow, somebody pushed it. And here you have half kinetic energy and half potential energy. Okay, so it's a 50-50, right? 50-50. When you have the ball falling on the ground, it will be at rest. So again, the kinetic energy has now becomes 0 and the potential energy is, what is it? Hold on. Potential is 0. Potential is 0. Potential is 0. I'm sorry. P is 0. And right before it falls, the kinetic should probably be at the maximum, right? Maximum. So that's basically the conservation of energy. Energy is not created, right? So neither does it dissipate. If it dissipates, it's going to dissipate in terms of heat, in terms of vibration. It will not go away just like that. Okay, it will transform into another form, right? So basically, you will use this equation, right, to solve for your impulse and momentum alongside the impulse, the principle of impulse and momentum equation, which we will look into right after this, right? Okay, so just bear in mind you have F equals ma, your equation of motion. You can use it whenever possible, whenever you feel necessary. And then you have your work and energy. Okay, you can use to solve problems whenever necessary that involves force. But if you happen to have a combo of force, velocity, and time, we'll get into it a little bit later. So force, velocity, and time in one question, then most likely you're going to use your principle of impulse and momentum. Okay. Okay, so that's a brief overview of what you can expect to learn in today's class. Okay. If we look at a bat, a baseball bat, usually we swing the bat, right? We just don't wait until the ball comes and hits the bat. Why? Because we want to reduce the time of contact between the bat and the ball. Okay, the faster you can produce the impact on the ball, the farther away the ball can go, right? So impulse is about driving a large force, okay, driving large force at small time, right? So why is this important? Impulse is something that we apply, for example, in crumple zone. You know crumple zone? You have a car, right? Car. Okay, please forgive me for the poorly drawn car, but this is the front of the car, right? So this is the crumple zone, okay? Crumple zone. Why is it a crumple zone? Because when you get into an accident, God forbid, but for example, someone gets into an accident, right? The first thing that is going to save his life is not the airbag, okay? The first thing is going to be the crumple zone, whereby the hood at the front here that is made up of aluminum, steel, whatever, right? That makes up the car. It will crumple. It will crumple like this. Okay? Dia akan remuk, They crumple. So before the force gets to your face, maybe a lorry hits you from the front, maybe, right? Before the actual force hits you on the face, the crumple zone will absorb the force by prolonging the time of impact. You understand? So the time there plays an important role to reduce the enormous force from the lorry or whatever that's going to hit the car. Okay, so that's why in terms of dynamics wise, we can design something so that the force, the impact on the object can be reduced by increasing the time taken for the force to reach the particle. You understand that? So that's why we have the concept of impulse. So there's a lot of things, right? A lot of other things. Why do parkour runners, parkour? Why do they fall from building but they don't get hurt? Okay, it's because they increase their landing time by doing rollovers to increase the impact time. So this is what we call the impulsive force. Okay, the force times time. Okay, that's going to be your impulse, right? How do we derive impulse? Okay, it's basically your F equals ma. Your F equals ma is basically everything that you need to deal with in kinetics of particle. If you look at here, F equals ma, a can be decomposed into dv over dt, right? Because from your kinematics, a equals dv over dt. And when you bring the dt over to the left hand side, right? Okay, and you integrate the impulse with respect to time, right? You give a, can you guys see this one? Yep, there's a t term there, t1 until t2. Okay, so because there's the integrand here dt, you have to put the lower and upper boundaries as t, the time, and the one left is m and the integration of dv. It's actually mdv here, but mass is constant for the particle, so we take it out, and what's left inside the integrand is dv. And the direction of impulse should follow the direction of the velocity. Okay, force, the impulsive force is going in the same direction of the velocity. Now, what this gives us is when you arrange stuff, right, you will get principle of linear impulse and momentum, which is equation 15.2. This is going to be, let's say, the main equation, or I would say rather the 15-3 is our main equation, right? This one is rearranged properly. Main equation for impulse and momentum, okay? So hold on to this one, right? You're going to hold on to this one, okay? And by the way, whatever is on the right-hand side, the MV, the nice term for it is called linear momentum. And whatever is inside this one, this term is called linear impulse. Okay, this one is also linear momentum, MV. Okay, the one in the middle is called linear impulse. Okay. So you can have just one source of impulse. You can have extra sources of impulse. And by the way, impulse is an external, external source. Okay. All right. Like I said before, you're going to hold on to this formula for your dear life when you start to answer problems regarding impulse and momentum. All right. I'm not going to go through this derivation of a rigid body. This is just the same thing. Instead of particle, it's going to be applied to a rigid body, because after the mid-semester break, you will also learn about rigid body. This is a rigid body. Okay, so we're going to focus on particles, but basically on rigid bodies, instead of velocity v, you're going to have the velocity of the body with respect to its center of the body. The center of what's the term called? Center of, was it the center of gravity? The mass center, sorry. Okay, the mass center. G. Okay, but we are going to focus on particles, so we are not going to deal with V sub G. So what we are going to hold on to is, again, our equation here, right? Which is the same one that I showed you before. So for rigid bodies, this one will be V sub G. That's it. Okay. All right, so I don't think we need extra more theory. We can jump right into the examples. So in the first problem, the 100 kilogram crate, okay, the mass is 100 kilogram, is originally at rest. This makes your life easy. What's that going to be? Your T1 is going to be 0, right? Because the T1 is half mv squared. And that velocity is going to be 0, and the entire term will turn out to be 0. Okay, smooth horizontal surface. That's going to imply no friction. Good. Then if a towing force of 200 Newton acting at an angle 45 degrees is applied for 10 seconds. You see, there's the time involved in this equation, in this question. Determine the final velocity and the normal force. Okay, you have to find the final velocity and the normal force which the surface exerts on the crate during this time interval. So the first thing you have to do is to resolve your free body diagram. As always, in our F equals ma, in our work and energy, you have to resolve everything in your free body diagram, right? So what are the forces involved? Can anyone tell me what are the forces involved? Weight, right? That is true. Weight going down like this one. What else? Normal. You guys are picking it up, yeah? Very good. So then what's the final one? P, right? What's the P? 200 newtons, right? So P is 200 newtons. So this is your complete free body diagram. Step 1. Cool. You get 2 marks for this one in your exam. Normally, okay? Wherever you have free body diagrams, then you'll get 1 or 2 marks, okay? Okay, if you get a free body diagram right, then the rest of your working will be correct, okay? Then what? Can we resolve things? What is this way? The force in this way is what? P cosine theta, right? Because it's close to the angle. And the one further from the angle is P sine theta. That's it. Easy. Okay, easy peasy. All right. Now what? Now we can apply the principle of what? Principle of impulse and momentum, right? PIM. I'm not gonna write everything. Principle of impulse and momentum, right? You know what? Let me just write it properly for the first time. Principle of impulse and momentum. So now we are gonna analyze in the X and Y direction. Makes our life easy, right? So let's see. In the X direction, let's put our convention plus this way and plus this way for X and for Y. Now for X direction, you're gonna say what's the principle of impulse and momentum? Let me just jot down the formula here. M times V, 1 plus summation of impulse force, which is F times dt from T0 until T. That's going to be M times V2. That's our equation that we are going to hold dearest to, right? Remember, I told you earlier, I hope I have copied it correctly, 15.6 here, right? This one. Hopefully I did that right, yeah? Yep, or this one, 15.3. If you have a single particle, then it's going to be just mv1. If you have multiple particles, you're going to have to add up all the m times v, all the linear momentums, right? Okay, by the way. So we have the mass of the crate. Let's put it 100 kilograms times what? What is the velocity? The velocity at point 1 is 0, right? Because it's at rest. Remember, we have figured this out earlier. So let's not write everything and just say it is 0. 0 plus, okay, what kind of forces do we have in the x direction? We have P cosine theta, right? P cosine theta. 200 cosine theta. And it's a constant force, right? It's a constant force. You don't need to integrate any function. You're just gonna substitute t minus t naught, which is 10 minus 0, right? That's gonna give us 10 seconds. So this is the time, right? And then that's gonna equal to the mass, which is 100 kilograms, times the velocity at point 2, which is the final velocity that is not known yet. I'm gonna give it a v sub x because we are gonna do our analysis in the y direction as well. So let's give that v sub x at 2. So the final velocity in the x direction,
14.4.
correct, 14 point, it's actually 14.1. So it's 14.1. The unit is meters per second. That was not too hard, was it? So let's do the y direction now. So going up, okay, same thing, principle of impulse and momentum. We're gonna have m v y, right? 1. You know what? I'm gonna put the x also here, mvx and mvx2. Sorry for the mess. Okay, hope you can understand that one. Equals the sum of forces, the impulse forces, Fy dt equals to m times the velocity in the y direction at time 2. Now let's plug and chug everything, right? So what do we have? This time around, it's not too straightforward, right? We have a lot of forces going on, right? Okay, so that let's put all the forces one by one. This one is gonna be, let's start with our 0. Okay, y is gonna be 0, right? Because at rest. And then the second one will also be 0. Why? First one because it's at rest, right? But the second one is because there's not gonna be any motion in the y direction. When you go after 10 seconds, you can imagine, right? If you just drag, you know, it's your hand over here, right? You're pulling at some angle, right? So you're gonna drag it behind you, the box. So not upward, it's gonna be forward. Nothing's gonna go upward. So the velocity in the y direction after 10 seconds is gonna be 0 because motion is in x. Is it too small? It's a bit too small. I'm writing over there. But you get it, right? The motion is in x. All right. Now what is left? This is a plus sign, I'm sorry. So what is left is the sum of impulse, right? So the impulsive force will be due to, let's see, p sine theta, right? So let's do p sine theta times t. What else do we have? P sine theta is positive, so because it goes in the upward direction. And then what? We have the normal force, right? Normal force is going up, it's positive. You times with time, multiply with time. It's confusing, times and time. So multiply with time. What else? The weight, right? So the weight is in the downward direction, so you're going to give it a negative mg, and you have to multiply by time. You see? Because it's always the force times or multiply by the time. Okay? The force multiplied by time. That will give you impulse. Okay? Force over a period of time, which is impulse. So always multiply with t. That's going to give you 0, right? So plug in all the numbers. So 200, blah, 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 sine 45 times 10 plus 10n minus 9.81. Let me just figure that out. Yeah, 9.81 times 100 is 981, right? So 981 times 10 equals 0. And you will have your n equal to some value, right? You can solve for the normal force, which is what the question is asking you. Okay, anyone like to attempt? 839.57. Yep, Saad, thank you very much. 839.6 newtons. This one is straightforward, eh? You just need to resolve the force. Okay, resolve all the forces using your free body diagram. That's why you have to master your free body diagram. Without it, you will have trouble generating your answers. Okay. All right, guys, are we ready for the second example? Yeah. Second example is quite similar to the first one. Okay, can the class tell me what are the forces that are involved? Weight. The weight, as always. Normal, as always. Friction. Friction, is it going in the A or B? B, right? Going up. So we have friction. And then we have a constant force P, right? So F sub F, frictional force, weight, normal, and P. So P is a function of time. Okay, we take note on that. Do we have anything else? No, right? So let's conveniently place our coordinate system based on the inclined plane's direction, right? This is going to be positive X, and this is going to be positive Y. Well, you can do your conventional X and Y like this one, X going this way and Y going this way, but that's going to make your life a bit harder, okay? You have to resolve all the forces based on the correct angle. So you see everything else is behaving well except for W, right? So frictional force is going in the X direction, although opposite, that's okay. P is going in the right direction, and also N is going in the correct direction, positive Y. The only thing you need to resolve is the weight, right? Which is going to be this one and this one. Okay, so if this is the angle here, the angle theta, then you know from experience that this is going to be your theta also. So hopefully you have done enough free body diagram exercises to identify that this is actually theta. Okay, otherwise you have to work out your way, draw all the triangles and the right angles and whatnot and figure out what is theta. Okay, I'm not going to go through that anymore. All right, so close to theta is W. So this is W cosine theta, and this one is W sine theta. Okay, so I have resolved all the forces right away on the free body diagram. Although in your exams, the free body diagram will only require you to draw the force, not the resolved forces. Understand? Okay. So in your exam, right, if you just show me that, this is W, this is F, or the friction, this is normal, and then this is P, that will give you full mark, yeah? No need to, let's say, show in the resolved direction. Once our FBD is completed, we can always work out with the principle of impulse and linear momentum, right? M V1 in the X direction, so that's going to be MVX. Let me just point out in the X direction. Positive, we are working on that one first. So MVX at time 1, okay, plus your sum of impulse from time 0 to time 1, or T, is going to equal MVX in the second point in time. Okay, if you're not sure what to write, just write down the principle or the equation itself first. Okay, so from there you identify, okay, what are the M, what are the V's, what are the F's, right? The forces, right? So the force in the X direction, let's do that one first. We have P, right? Hold on. The first term V1, is it starting at rest or not? No, so it has V1 is some velocity, right? 3 feet per second. So you're not gonna simplify it to 0. So M is 50 pounds, 50 over 32.2. The velocity of X at point 1 or time 1 is 3 feet per second, okay? Now this is the challenging part. First of all, what is the force that acts in the X direction? We have P, right? P is in the positive direction, so it's going to be positive 20t, and you have to, like it or not, integrate it from t equals 0 to t equals what? 2 seconds, right? 2 seconds after, okay, 2 seconds, right? That will give you something. And then let's see, we don't stop there, right? We have P. What else? We have W sine theta, right? W sine theta, which is the byproduct of the weight. So it's a constant anyway, so we're not going to integrate it. Rather, we will add it to the impulse, W sine theta times T. What else? We have frictional force, right? Frictional force going in the opposite direction, negative mu sub k times n, and then you would multiply that by time. You see, consistently, every term in the middle here is multiplied by time, and time. And that would equals to 50, which is the mass, over 32.2 times V2, okay? The velocity in the X direction at time 2. Okay, we will get not an answer, but an expression, because we have V sub X at point 2 or at time 2, and then we also have normal direction or normal force, which is not solved for us yet. So let's figure this one out. So hopefully everyone arrived to this one, yeah? 4.658 plus 40 plus 50 minus 0.6n equals 1.553 V in the X direction at time 2. We are now going to apply the equilibrium of forces, okay? F equals ma in the Y direction. So you see, when you start to learn a lot of kinetics theories, you can start to use or apply many equations. You have a lot of tools at hand. Okay, before this, you only had kinematics equation. You were struggling to find out the velocity and whatnot. Now you can simply apply your F equals ma, right? Number 3, step 3, F equals ma, right? So in the Y direction, you would not have any impulse, so it's not applicable for the principle of impulse and momentum. So you're going to use your equation of motion, which is going to give you the sum of force in the Y direction equals to mass times acceleration in the Y direction. Okay, can you please go on the top? So what will that give us? So we will have the normal acting positive Y direction minus W cosine theta, right? W cosine theta is going downwards. W cosine theta, that will equal to 0. Why? You will not have acceleration in the Y direction. If this is not a curvy linear motion, where you have acceleration in the normal direction, this is a rectilinear motion. You have a straight inclined plane. So there's definitely not going to be a acceleration component in the y direction. Right, so your n is gonna be mg cosine theta, right? Okay, I just simply brought w cosine theta to the right hand side. So w equals mg, so cosine theta multiplied by that will give you how much? The normal force.
135.
No, we are not talking in Newton. Okay, we are talking in the US units.
Oh.
So you see, W is just basically the pound force of the given particle. So you see, what's this? The weight is 50, just 50. So it's gonna be 50 mg is 50 because m is 50 over 32.2 and g is 32.2. Okay, so it's gonna be 50 cosine 30. So n will turn out to be 43.3 pounds.
So gravity in US is
Yep.
gravity in US units.
In US unit, yeah. Yeah, acceleration is 32.2 feet per second squared in the US units. Okay. Can you work out what is going to be your velocity in the x direction at time 2? Yes, right? You have your n worked out. So you're gonna obtain your Vx sub 2, right? V sub x sub 2. So the velocity at time 2 is gonna be, so I'm just gonna give out the answer, 44.2. Yes, I heard that correctly. 44.2 feet per second. All right, let's see. In class, problem number 3. So this time around, okay, this time around it's a bit different. Okay, before this we had multiple forces going on, an inclined plane, constant force, friction force. This time around, if it involves pulleys, you have to use your pulley kinematics. Okay, so you know what, when you see a pulley question, always start off with the kinematics. It's very easy. Okay, at least you get some marks there. You know what I'm saying? If you cannot figure something out, just do the normal exercise that we did last time. You see, you draw the rope. Okay, you draw the rope like this one. You see, and you find out what is the length of the rope, right? Isn't it? So what is the length of the rope? Length is equals to, if you're given SA like this one, right? This one is SA, this one is SA, and this one is S sub B. You wouldn't care much of whatever goes around the pulley, right? Because they're gonna be the same length anyways. So we're not interested in that. So that's gonna be S sub A plus, sorry, two S sub A's, right? Plus S sub B. Okay, if you are ever in doubt when you see pulley-like problems, always start with the kinematics. It's not gonna affect anything. It's not like if you resolve your free body diagram wrongly, you will affect the rest of the things, right? But this one is sort of like independent exercise. So if you differentiate the total length, that would be 0. You differentiate the S, it becomes velocity. And if you differentiate velocity, it will become acceleration, right? But we're not interested in acceleration because the question asks us for velocity only, active velocity. So we are fine there. And from here, we can say VA equals minus VB over 2, right? So that's that. So that's the kinematics. That part is done. Let's just box that one. Okay. So again, as always, we start with the free body diagram, but just for pulley systems questions, I always like to get the kinematics out of the way first. So this is the kinematics of pulleys. Okay. Now let's draw the free body diagram. this time around in green, right? So let's see. So block A, FBD. So block A. Is it too bright for the guys at the back? I think I'm gonna turn the color into darker one, yeah. Okay. FBD. Block A. All right. Block A, you see, we can start off with the pulley itself, the roller itself. Okay, just to give you an idea that there's tension in the cable, right? Okay, there are two sides of the cable, and then you have the weight that is dangling from the cable. And basically, you will have, if this is block A, you can simplify it into two tension forces going upward and one weight force going downward. All right, that one is for block A. Let's stick to this one. This one is the simplified version of the FBD. How about block B? Block B, we have the block itself, and then the tension, 1 unit of tension going up, then 1 weight going down. Okay, so now once your free body diagram is done, you can right away jump into your principle of impulse and momentum. So we will do it block by block. Okay, make our analysis a bit easy. Let me just drag these guys to the right. Just bear with me a second. And let's get back to business. So we have, usually for the downward direction, we will have positive, right? Positive. In our pulley-based questions, we have this way is positive, right? So let's decide that as our convention for position. So let's say downward positive for block A, right? For block A. So the principle of impulse and momentum applied at block A first. Later we will apply at block B, okay? Again, the formula is M V. So M is the mass of block A. V is the velocity of block A. MAVA plus, okay, what do we have in the free body diagram for block A? We have W, which is positive, going down, and then we have T. Okay, impulse is always, remember, impulse is force multiplied by time. Okay, so we have the force here, and then we have the time here. Okay, unless it is a variable force, you cannot simply multiply by time. You have to integrate. But the rest of them are constant. Weight is a constant. Friction force is a constant. You know, others except for variable force, they are constant force. Now, what else? Tension, we have 2T, but it's in the opposite direction, right? So it's minus 2T times or multiplied by time. That's it, right? For our impulse force that are involved in this particular problem. Now we're going to have that equals to mass of block A times the velocity of block A at point 2, or at time 2, I'm sorry. So at time 1, we have V sub A sub 1. So that's how you set up your principle of impulse and momentum equation. The rest of it, they are easy. The rest of it is just plug and chug, right? So put in all the values and you will find the answer. So can we figure this one out? So let's see, yeah. The system starts at rest. Does it?
Yeah.
Yep. So it was released from rest. So this one comes 0. The weight of block A, W sub A lah. W sub A. So the weight of block A is mg. Block A is 3 kilograms. 3 times 9.81 times T is 6 seconds. 6. minus 2t, 2 capital T, and then small t. So 2 times 6 is 12, minus 12t equals 3 times V sub A at time 2. So not so pretty. Orang putih cakap not so pretty. So not so nice. The equation we have here, we have two variables, but one equation, yeah? Even the kinematics equation cannot help us. So we have to do one more, okay? One more PIM, principle of impulse and momentum. Now for block B. Hopefully this one will give us an extra equation so that we can solve for all the simultaneous equation. Okay, now for block B, going down is positive. Mass of block B times the velocity of block B at time 1 plus all the force that makes up the impulse, which is positive W times or multiplied by time minus T. Okay, we have positive W going down, minus T going up. Okay, so minus T multiplied by small t. That's going to equal mass of block B times velocity of block B at time 2. Okay, at 6 seconds. Okay. Again, let's put this one to 0. And this one, this time around, is the weight of block B, right? So the weight of block B is 5 kilograms times the gravity, mg, multiplied by 6 minus 6 capital T, tension. Okay, we plug in the mass 5 times V B sub 2. Now we have, fortunately, 3 variables and 3 equations. So we must be able to solve this one. Let me just box everything. We have this guy. Then we have, let me just mark that as equation 1. We have this guy. Let's mark that as equation 2. And then we have this guy. And then let's mark that as equation 3. Okay. So there's many ways to solve this. Do you like it as an exercise or do you want us to solve this together? Together, eh? Okay, let's solve this one together. 1 into, okay, substitute 1 into 2. So 176.58 minus 2t equals negative 1.5 V sub B. Okay. Sorry, minus 12, is it? Sorry. Let's call this one as 4. This one is 4. Then let's say 4 times 2. So you multiply equation 4 by 2. You will see why, eh? You will see why later. So this one you have 588.60 minus 12. Am I doing right?
We have to multiply 2 with equation 3.
Oh, equation 3. I'm sorry. Yeah, equation 3. 3 times 2 minus 12t equals 10 V sub B. Okay. That looks like something. Wow. What a shape there. Okay. That is fine. Okay. Can you see 4 and 5? You can eliminate the tension, right? So 4 minus 5. Okay, you will get minus 12t minus negative 12t. You will have 0. So you can solve for V sub B. V sub B at time 2, isn't it? Let me just be very particular here. Okay. Okay, so 176.58 minus 588.6 is going to give you negative 412.02. Negative 12t minus negative 12t, that's going to add up to 0. 1.5 VB minus 10 VB is minus 11 V sub B. Okay? Eventually, you will get the answer of 35.8 meters per second. And that's going to be your final answer. Okay, let's continue. Okay. Conservation of linear momentum for a system of particles. What happens when you just have the particles colliding with each other without any external force? Okay, before this we discussed that the impulse is affected by the weight, what else? The external force, the applied force, the variable force. The impulse was affected by what else? The frictional force. But let's say you have just two particles without any external force acting on it. They are just there hanging out and going into each other without applying any external force on the body. So we don't have the middle term here. Okay, what will that give us? That will give us just the linear momentum, right? Just the linear momentum. And you see, without the impulse in the middle term here, you will see that the linear momentum is conserved. The linear momentum at time 1 is going to equal the linear momentum at time 2. Okay, so that is what we call the conservation of linear momentum, whereby the sum of the external impulse equals 0. Okay, so this one happens often when particles collide or interact with each other. Okay, so you can, for rigid body, you can substitute V sub I with V sub G, which is the velocity of the mass center. Okay, but we are not interested in that one for now. Okay, for now we are just looking at particles, not rigid bodies. Okay, so that's it, right? So without the impulse, without the external forces, you're just going to look at the linear momentum, which is conserved from time 1 to time 2. So let's look at how things appear when there are no external force. Okay, so let's say, for example, this one, the cart on the left is by default when this problem starts, it is moving. Yeah, it is already moving by 1.5 meters per second, and it encounters another tank, a truck or a boxcar, tank car moving 0.75 meters per second towards the opposite direction. So in this case, right, where there was no external force, right, that is working on the particle, what you see is, let's draw a free body diagram, right? So free body diagram, what you see is this car, okay, and this tank. At one point, okay, they will collide, right? They will collide and they are coupled together, meaning they stick to each other. So once they collide, they are sticking to each other. Let me just write down a note here. Change pen, please. Note. Okay, the coupling force, okay, is internal to the system. What are the coupling force? You see, when they collide each other, they have, from A, there's a force and there's another internal force from B, F prime, isn't it? Oh, no, negative F. Okay, so these forces, they cancel out each other. Okay, the coupling force, F is the coupling force. It's the internal force. Okay, when they start to hit each other, B will when it hits A, it will result in a force experienced by A, and that force is negative F if we take positive this way. And B will experience an internal force by the collision of boxcar A. Okay, so it will experience an internal force from this side, and that force we call F. It's positive F. But because they have the same magnitude, they will cancel out each other. They cancel the internal force cancel out. Okay. So now we have the mass of truck A, which is 15 times 10 to the power of 3 kilograms. Why? Because M is mega. Mega is 10 to the power of 6. And gram is 10 to the power of minus 3 kilogram. Okay, because 1 gram is 1 to the power of minus 3 kilogram. We have car A moving at, hold on, VA is 1.5 meters per second. The mass of car B is 12 times 10 to the power of 3 kilograms. And the velocity of B, guess what? Is it positive or negative? Negative, right? Because it is in the opposite direction. Okay, so we have decided that our positive convention will be towards the right. And therefore, if we have the velocity of B is 0.75, it's actually negative 0.75. Why? Because velocity is a vector. It has magnitude and direction. If you have a negative direction, you have to take it into account and you have to put the negative sign there. We are now looking at a problem of conservation of linear momentum. You see, this one, the conservation of linear momentum. Okay, so mv1 equals mv2. That's it, right? Very simple. So number 2 is, the second step is conservation of linear momentum. So what does conservation of linear momentum tells us? So mass times velocity at point 1 is equals mass times velocity at point 2, right? So like this one. But unfortunately, you have just one particle. You have to consider also the tank B. So you have to add m times v of tank B. That's gonna equal, so because when they have collided, they couple together, right? After they collide, they couple together. You see, after collision, they couple together, meaning they go after the collision in the right direction with a situation that they are sticking to each other, right? Yes, so they're going with the same velocity, with a common velocity. So they're gonna add up the mass. So this is A and this is B. So they stick to each other. They have a combined mass with a common velocity. So let's plug in the numbers, right? So we have 15,000 times 1.5 plus 12,000 times negative 0.75 equals 15,000 plus 12,000 V, right? Equals V. So V will turn out to be V at time 2 lah. V at time 2. So V at time 2 is equals 0.5 meters per second. So if you plug in the numbers in the calculator, the velocity will turn out to be 0.5 meters per second. Okay. And positive sense is in the right direction, towards the right. So that answers the first part of the question. The speed of both cars just after the coupling. Okay, the speed of both cars, which is the velocity at time 2, is 0.5 meters per second. Cool. So first question is down. Now the second question. The average force between them if the coupling takes place in 0.8 seconds. So if the question asks for average force, you actually have to isolate the free body diagram. You see, when you did the free body diagram, okay, one particle collides with the other and both particles will give out some force to each other. So when you consider the opposite forces, they will cancel out. So in order for you to find what is the actual force, you have to isolate the free body diagram. Okay, you isolate the free body diagram. Isolate it. It doesn't matter. You can isolate just A or just B. Okay, either one. It will give the same answer. But the only difference is you have to look at what is the external force that causes the impulse. If you isolate A, right? If you isolate A, the external force that gives the impulse is F or negative F. It's going to be actually negative F. F is the force from within A. Negative F is the force from outside, which is from B. So remember, impulse is always the external force. Okay? Something, in this case, you will draw your FBD. Okay, for isolation of A. You can isolate B as well, no problem. So let's decide on one thing, which is we are going to isolate particle A. Why do we need to isolate? Because if we combine like the top free body diagram, we will not get the force. Okay. So let's pick A, right? So let's pick A. This one is block A. Now the force, the external force that acts on block A is the negative F there. Let me just put another note here. Note that isolate the particle to get external force for impulse. Now we have the free body diagram. We can straight away go into the principle of impulse and momentum. So can I just isolate my working here? Okay, so let's continue down here. So again, our principle of impulse and momentum will give us mv at 1, because we're looking at block A, right? So everything is subscript A. At time 1 plus the sum of forces times dt equals m a va at time 2. Okay, principle of impulse and momentum. Just apply it. Now we plug in the values. So 15 times 1.5. Okay, because it's minus F, we are considering in this direction, right? So minus F, what was the time? Time is 0.8. 0.8, yes. 0.8 equals 15 times 10 to the power of 3, 0.5. Okay, V2 was 0.5. Remember, we solved earlier. V2 was 0.5. So you're gonna find out what is the force here. Average force is some value. Okay, the force is going to be 18.8 kilonewtons. Yeah. Any question? So if no one has any question, then let's call it a day. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.